Faraday's law and induced electric fields 1. In using Faraday's law for a loop of metal wire, there are 4 things that all happen simultaneously, although it is helpful to think of them as happening in a linear sequence. In the circles below, list those 4 things that happen and in a thinkingly useful sequence. Well, whenever we use Faraday's law, what happens is the magnetic flux is changing. And whenever the magnetic flux is changing within a loop, there is an electric field that is induced at the edges of that loop. And whenever there's an electric field that is induced, that means that there is an EMF or a voltage that is induced. And since we're talking here a metal wire, if there's an induced EMF, the metal will have a small amount of resistance anyway, and we will get an induced current. For each loop below, draw and label electric field vectors to show the direction of the induced electric field. This electric field will be in a direction in accord with Lenz's law, which says that whatever is happening with the flux in the loop, the induced electric field will attempt to undo that change. We can think that nature doesn't like change. So in the leftmost figure here, we see that the magnetic field is coming out towards us, indicated by the dots, and it's increasing, which means the flux out of the page, I'm using my right thumb now, is increasing. And nature doesn't like change. So we're going to fight that increase with our thumb. And which way do our fingers curl? Clockwise around this loop. So if we want to know the direction of the induced electric field, we're going to have to go clockwise. And we could put any number of those vectors here, but I'll just draw 3 of them, okay? How about the next one? Now we have the magnetic field going into the page, and it's weakening. We got our thumb. The magnetic flux is directed into the page, but it's getting weaker, and we don't like that change, so we're going to try and help out with our thumb. Again, clockwise. The electric field at the perimeter here is going to be directed in a clockwise sense. How about for the next one? The magnetic field is coming out towards us, so that means that the flux is directed out towards us, and it's getting weaker. Nature doesn't like change, so we're going to try and help that weakening flux with our thumb. I'm thinking counterclockwise this time. The electric field and the EMF and the induced current, if we have a metal loop, are all in the same sense. Last one. Here we have the magnetic field directed into the page, and it's increasing. We're getting more and more magnetic flux into the page, and we're going to fight that change with our thumb by pointing the thumb up. And I think, again, we're going to end up going counterclockwise for this one. Tangent to the loop at every point. Write the entire Faraday's law equation for one loop. Hint, there should be 2 equals signs in the answer. We are generating an induced EMF, and if we only have one loop, then we don't have to put N in front. So that's part of it. And then the other part is it's the dot product of the electric field going around the edge of the loop. What's the equation for finding voltage using the path integral of the electric field? We did this sort of thing when we were dealing with capacitors. And you can see that these equations are very similar. Voltage, we've got a path integral of the electric field. In what important way do these integrals differ? In other words, what does it mean that the integrals are written as they are? The integral sign without a circle means we start the integration at one place and end at a different place. That's what we did when we were using that equation, for example, with capacitors. We started usually at one capacitor plate and we ended at the other. The integral sign with the circle in there means that we're going to end the integration at the same place where we started, and that's the one that we're going to employ in this case, because that electric field, if you remember those pictures we just drew on the previous page, we're just going around the circle and we're ending up at the same spot where we started. That answer has important implications with regard to the nature of the induced electric fields that we drew in part 2. Let's complete the statements below which describe any induced electric field. Any induced electric field E is a non-electrostatic electric field, which means that it is not caused by a buildup of electric charge. Or maybe another word besides buildup, a separation of electric charge. There's no buildup, there's no separation of electric charge whenever we have an induced electric field. It's also a non-conservative field, which means that the path integral of the field along any closed path is not equal to 0. This in turn means that forces exerted by this field have a strong tendency to increase the internal energy of material objects, i.e. generate heat. And finally, an induced electric field E can be said to exist at a particular location even if there is not a material object at that location. True.